Math 2414, integration by parts. Integration by parts, example 1. In the previous video, we essentially derived this rule, if you want to call it a rule. It's more like a way to transform one integral into another. The integral of u dv equals uv minus the integral of v du. But we never actually did an example, we just built a technique. I'm going to spend a few videos working some examples and giving you some ideas on how to recognize when to try this and how to approach it once you've decided that this is the technique you're going to try. For the first example, we're going to integrate the integral of x sine x dx. When you integrate, your first course of action is typically, is there a rule that this fits? If you go and review, I forget which video it was in the previous series, the integration rules, none of them look like this. There was one that said the integral of sine of x, which was negative cosine of x. And if we had x by itself, its integral would just be 1/2 x squared. But because we can't integrate a product term factor by factor, we can't just say 1/2 x squared times negative cosine of x. Plus, we don't have a rule that structurally resembles this. So that's the suggestion that we can't just straight up integrate. Can we do a substitution? Well, you could try to do a substitution, but there's no substitution that's really going to change the structural flaw with this integral. The structural flaw being it's the product of two things that we can integrate individually, but not necessarily together, at least not yet. So what suggests trying integration by parts? Well, if you remember that the word parts actually means part of a multiplication problem, aka a factor, this is a multiplication problem. So it has parts, and maybe we should try integration by parts. Now, once you've decided to try integration by parts, your next move is try to identify which parts of the integrand you're going to call u and which part you're going to call dv. In other words, you're separating this into the product of two parts, one that is an undifferentiated function and one that is a differentiated function. When you're making the decision on who to call u and who to call dv, and by the way, the dv will always include the dx because something already got differentiated. But when you're analyzing this and trying to split it into two parts, think about what's going to happen with these parts eventually. This v, whatever we call dv, eventually has to get integrated to turn it back into v, both here and here. So whatever you call dv has to be integrable and preferably easily integrable, and both of these are easily integrable. Whatever you call u eventually is going to get differentiated, so whatever we call u has to be differentiable. Well, technically speaking, we can differentiate anything with enough patience and enough rules. So I'm not too worried about selecting who I'm going to call u, the guy whose derivative I'm going to take. I'm more concerned about who I'm going to call dv because I have to integrate it to take it back to the v. Additionally, when you make your decision on who's going to be the u and who's going to be the dv, you want to think about what the second integral is going to look like because we want to fix any problems that are preventing us from integrating. The problem here is we have a product and that product doesn't fit an integration rule. Knowing that I'm going to take the derivative of part of this, whatever I call u is going to get differentiated. I'd like to pick something that will become simpler when I differentiate it. Of these two parts, which one becomes simpler upon differentiation? And the answer is the x. If we take its derivative, it's just 1. That's a great part to have in an integral. So there's a variety of ways to make the decisions. What are you going to call u and what are you going to call dv? But the two driving factors should be, whatever I call dv, I need to be able to integrate easily. Maybe not easily, but eventually. And whatever I call u, it would be ideal if it would get simpler when I took its derivative. In fact, this is as simple as it could get because its derivative would become 1. So let's set this off. When you do an integration by parts problem, the very first thing you want to do is to declare what u and dv are going to equal by usually saying something like let u equal something and dv equal something. Now you don't have to physically literally dissect the integrand, but I'm going to for the first few examples. I'm going to let u be just the x. And again, my reason for that is I'm going to need its derivative in a moment, and the derivative of x is very convenient. And I'm going to let dv be the rest of it. All parts of the integrand need to be either under u or dv. So we're going to let dv equal sine x dx, which is easily integrable. Its integral, antiderivative, is negative cosine of x. All right, once you've made these declarations, think about the pieces that we're going to need to disassemble this integral and reassemble it into this expression. We need to know u, which I already have. We need to know v, which I don't have. And we need to know du, which I don't have. But I know things about u and v, and I can get the missing pieces. Specifically, to find the du to build this piece of the right side, I just take the derivative of whatever u equals, which in this case is 1, and then put the dx on it like we're doing a substitution. But how do I get the v when I know what dv is? And the answer is you integrate. The u gets differentiated, the dv gets integrated. And if we integrate sine of x, we get negative cosine of x. Or rather, I should say, if we integrate sine x dx, we get negative cosine of x. I am going to write to the side of this because here's what actually happens. V is equal to the integral of dv. Think about it. Integral, derivative cancel each other, which in this problem is the integral of sine of x dx, which is equal to negative cosine of x. Now technically this picks up a plus c here because it's an indefinite integral, but at the end we'll just stick the plus c on. You don't have to write all the stuff in red, but that's the reason v is equal to negative cosine x. Whatever you call u, you differentiate. Whatever you call dv, you integrate. And now I have all the necessary pieces to build the right side of the integration by parts rule. So this means that our integral of x sine x dx, the original integral, is equal to, and I'm going to write the expression for integration by parts in blue, just above just a little higher here, u v minus the integral of v du. Or you can just look over here, and I'm going to build that expression with the u's and the v's and the du that we have above in green. We start with u times v. U is x. V is negative cosine x. So if I multiply those, I get negative x cosine x. Minus the integral of v du. V is negative cosine x. Not sure if I really need the parentheses around it. And du is just 1 dx. I'm going to write 1 dx, but normally I wouldn't bother writing that 1. Have we answered the integral? No, we've changed it. Let's clean it up and see where we are now. We have negative x cosine of x. We have a minus and negative, so we can make that a plus. Integral 1 times cosine of x, which is just cosine of x, dx. And again, we haven't finished the problem, we've changed the problem. But notice that the integral we have now doesn't have the thing that was preventing us from being able to do this integral, namely that x in front. We know the integral of cosine x. It's an integration rule. The integral of cosine x is sine of x. And when you complete the second integral, that's when you can pick up the plus c. And so we have the integral of x sine of x. Again, the hardest part about integration by parts is the setup. Identifying the u and the dv, and then following through with your plan of attack. The u gets differentiated to become du, the dv gets integrated to become v, reassemble the pieces in this expression, and then take a look at the integral you just set up, and if you're lucky, you can finish it right then and there. We could check the answer by taking the derivative. I'm not going to do that. I strongly recommend pausing the video and trying it. You would need to invoke the product rule here. Of course, the derivative of sine is cosine, the constant would disappear, but when it all cleans up, everything will cancel except for an x sine of x. It's worth mentioning that you can use integration by parts on definite integrals, such as this integral from 0 to pi over 2. But using the fundamental theorem of calculus, we just have to find an antiderivative evaluated at the limits of integration and then subtract the results. Well, this is the exact same integrand as before, and we already have a general antiderivative with the plus c. But for the fundamental theorem of calculus, we only need any antiderivative, so this constant could be anything we want. I choose 0. The antiderivative is negative, or an antiderivative is negative x cosine of x plus sine of x. And we're going to evaluate this from 0 to pi over 2. Hope your trig skills are honed. If we substitute pi over 2, we get negative pi over 2 cosine of pi over 2 plus sine of pi over 2. And if we substitute 0 minus, we get negative 0 cosine of 0 plus sine of 0. And now we have to evaluate those trig functions, which should be pretty easy, especially if you're familiar with your unit circle. And when, just a reminder, you should know all of your trig, especially unit circle. So I'm not going to waste time explaining why these trig functions values are what they are. If you need some help, let me know. I'll hook you up with some content. But without further ado, cosine of pi over 2 is 0. Sine of pi over 2 is 1. Well, 0 times anything is 0, but cosine of 0 is 1. Sine of 0 is 0. So let's see what's left. We're left with 0, because negative pi over 2 times 0, plus 1, so we got 1, minus a bunch of zeros. So this integral just ends up being a piddly little 1. We're going to look at a few more examples of integration by parts, but they're all going to kind of run the same course. Find the u, find the dv, calculate du and v, rearrange the pieces according to the rule in the red triangle, red rectangle over here, and then hope that the second integral that you set up right here is easily integrable. And if it happens to be a definite integral, then just follow through with the evaluation at the limits of integration and subtract the results.